All right, let's talk about the computer. Not just the box on your desk or the phone in your pocket, but the entire story behind it. It's a journey that starts somewhere pretty unexpected. Not with silicon, but with a really simple, powerful question. Before screens glowed?
Yeah, before keyboards made that satisfying click.
And way, way before our whole world went digital, there was this one single driving idea. And this was the question. Can a machine help us think? I mean, just pause on that for a second. That's the spark that lit the fuse for this whole revolution. It's a quest, really, to build a tool that could actually amplify the human mind. And our story? Well, it begins long before anyone had even heard of electricity. So let's start at the beginning. We're talking about a time with zero electricity. None. If you wanted to build something that could think, it had to be physical. You had to be able to touch it. It had to be mechanical. Long before we had calculators on our phones, the big challenge was just, how do you wrangle all these numbers? So what did we do? We built tools. The abacus, right? That turned these abstract numbers into something you could physically move. Then, fast forward to the 1600s, and you've got these brilliant minds like Pascal and Leibniz. They're building these incredible machines with gears and wheels to do the math for you. And that was a huge breakthrough. It was proof that a part of thinking, at least calculation, could actually be automated, mechanized. Okay, but the real game changer, that came in the 1830s from this visionary guy named Charles Babbage. See, he didn't just want another calculator. He was dreaming way bigger. He imagined a machine that you could program, a machine that could solve pretty much any problem you threw at it. He called it the analytical engine. And honestly, it was the blueprint for every single computer that would ever be built. And this is the part that just blows my mind. Look at these concepts. They are so incredibly modern. He imagined a processor, he called it the mill, to do the actual work. He thought about memory, the store, to hold the numbers. He even figured out how to get information in using punch cards and how to get it out with a printer. This entire framework was laid out more than 180 years ago. It's wild. But it took someone else to see the machine's true potential, its soul, really. And that person was Ada Lovelace. She had this incredible insight. She realized, hey, if this machine can manipulate numbers, and you can represent anything with numbers, like letters or music notes, then it could process, well, anything. This quote nails it. She's saying it's not just a number cruncher, it's weaving patterns just like a loom. In that moment of understanding, she basically became the world's very first computer programmer. So, Babbage's amazing engine, it was never actually completed. The technology of his time, all those gears and levers, just wasn't precise enough. The idea was brilliant, but it was ahead of its time. It had to wait for a brand new force to come along and give it power. And that force, it was electricity. And wow, when electricity entered the picture, it created this massive shift. It's like night and day. We went from clunky, physical gears turning slowly to invisible, abstract signals zipping around at almost the speed of light. Suddenly, the limits weren't about physical friction anymore. The only limit was our own imagination. And during World War II, this new power was completely unleashed. We started building these colossal machines, like ENIAC. I mean, these things filled entire rooms. And their power, their secret sauce, came from thousands and thousands of these little glass bulbs called vacuum tubes. Each one was basically a tiny, super fast electrical switch. And right here, this is the simple, beautiful, elegant genius behind everything. Think about it. An electrical switch can only be in one of two states, right? It's either on or it's off. So let's just give those states a name. We'll call on a 1, and we'll call off a 0. And that's it. Seriously, that's binary code, the fundamental language of every single computer on this planet. Okay, so we've got this language of ones and zeros. Awesome. But how does a machine actually use it to, think? To get that, we've got to pop the hood and take a look inside the computer's brain. And this is it, the central processing unit, or the CPU. Now, it doesn't think like you and I think. It doesn't have feelings or ideas. But what it does do is perform billions, with a B, of simple yes or no decisions every single second. And it's out of that ridiculous speed that all the complexity we see on our screens emerges. So the CPU has this constant, relentless rhythm. It's like a heartbeat. First, it fetches an instruction from memory. Then it decodes that instruction to figure out what it's supposed to do, and finally, it executes the action. Fetch, decode, execute, over and over and over. And we're not talking a few times a second. We're talking billions of times per second. It's the very pulse of the machine.
Now, those early computers, the room-sized ones, they were absolutely revolutionary. But let's be honest, they were also huge, super unreliable, and they guzzled power like crazy. The next great leap had to solve that problem. It was all about shrinking them down, from the size of a room to something you could actually hold in your pocket.
And this is the invention that made it all happen. The transistor. Born in 1947, this tiny little device did the exact same job as one of those big, clunky vacuum tubes. It acted as a switch, but it was infinitely smaller, way faster, and so much more reliable. I mean, it wasn't even a contest. The transistor just completely destroyed the vacuum tube on every level. It was tiny and tough, not big and fragile. It ran cool instead of burning hot. It was super reliable. But maybe the most important thing, it could be mass-produced for cheap. And that, right there, paved the way for putting computing power into the hands of, well, everyone. And this is where things get truly mind-boggling. Thanks to this constant process of miniaturization, a single high-end computer chip, like the one in your phone right now, can have over, get ready for this, 50 billion transistors etched onto it. 50 billion switches, all firing in perfect sync. That is an absolutely staggering feat of engineering. But here's the thing. All that incredible hardware, all those billions and billions of transistors, they're just a collection of really, really fast, but ultimately dumb switches. They don't know what to do on their own. They need instructions. They need a ghost in the machine to bring them to life. And that ghost, of course, is software. It works in layers. At the very bottom, you've got programming languages, which are basically translators that turn our human logic into the ones and zeros the hardware can understand. On top of that, you have the operating system. Think Windows or Mac OS or Android. And its job is to be the manager, making sure all the hardware and software can talk to each other. And then finally, on the very top, you have the applications, the stuff we actually use to get things. So think about it. When you just tap an icon on your phone, it feels so simple, so instant. But in that tiny fraction of a second, what you're really doing is kicking off this invisible symphony, an incredible dance of instructions and logic, with electrons moving and voltages changing, all coordinating those billions of transistors. It's a beautiful hidden masterpiece of physics and logic happening every single moment. So here we are. We've gone from moving beads on an abacus to interlocking gears in a box to firing electrons through circuits, and now all the way to artificial intelligence. It's been an unbelievable journey, but it leaves us with one final big question to chew on. Is this the story of how a machine evolved? Or, as we built these ever more powerful tools to help us think, is this actually the story of how our own thought evolved right